today we're going to do section 6.4 on page 586. Now first, let's remember what we learned last time. What does the logarithmic function mean? The logarithmic function log of b base b of y equals to x means exactly that b to the x power equal to y. That is, b to this thing equals to what you're taking the log of. So that is still something that you might be trying to get used to. Okay, it's kind of a roundabout way of saying this. These two statements are exactly the same. That is, they mean the same thing. It's just saying it in a slightly different way. And but we are going to today learn how to plot the graph of the logarithmic function. And b is always bigger than 0 for our purposes. Okay, we don't care when b is less than 0. It just doesn't work out well. And so with that, let's consider example 1. Okay, let's we have log base 2 of x plus 3. Now to find what the domain is, that is, what does this have to be? Now when you notice that the definition of the log means that y is equal to b raised to the power x, right? Where b is bigger than 0. Now, which means b raised to the power x, whether x is positive or negative, being that b is positive, y is always positive. And that's the domain of the logarithm, okay? The y is, which is in this case x plus 3, that is what's in here, it will always be positive. That is, the domain is simply x plus 3 bigger than 0. Is the domain, or another way of saying it is x bigger than, move the 3 over here, becomes minus, and it becomes minus 3. That's basically the domain. And another way of writing this, if you want to do it the book's way, is called minus 3 comma infinity. That means the domain starts at -3, not including it. That's what the parentheses means, and you can go forever in the positive direction towards positive infinity. All that is in the domain. So that is example 1. And then and example 2 is the same way. It says, what's the domain of log of 5 minus 2x? Now this log doesn't have a base number, okay? It just says log. It doesn't say what the base is. If it doesn't say base, it means base 10, because base 10 is called the common log. So, but the same principle applies. In example 2, that means it means whatever is inside the y value in previously it was x plus 3, now is 5 minus 2x. Either way, whatever it is, it has to be bigger than 0. That's the domain, which if you solve this equation, then let's move this over here, okay? Because we will keep our x's positive if possible. So this becomes 2x, and then that's 5 here. And now it reads 2x less than 5, okay? If you read it, you know, this is the smaller side, and that's the bigger side, see, of the inequality. So then it means x is less than 5 over 2. You can divide positive numbers across inequalities as if it's the equal sign. So push the 2 down, okay, across the inequality to the bottom of the division line, and that's the answer. You can also, this thing is also written like this. As long as you keep the arrows right, then everything's correct, okay? This reads 5 over 2 bigger than x, or x less than 5 over 2, which is, if you draw it on the number line, that would be minus infinity, going all the way up to 5 over 2, but does not include it. So it's parentheses. If you want to include it, that will be the bracket. But right now, we don't include it. Yeah, because this cannot be 0, okay? It has to be, this number has always to be positive, because b raised to some power cannot be 0, okay? I mean, b is a positive number, so whatever power you raise it to, it will never be 0. So so the 0, you cannot put an equality sign here as a result. That is why it cannot be 0. Y has to be positive without being 0. And anyway, which positive means you're not 0, okay? Because 0 is neither positive nor negative. Anyway, so that's example 2. Yeah, that's the correct answer. And let's look at the next page. To graph the some kind of okay, let's look at this thing for a second. Now to graph the logarithmic function, we we remember that it's similar. Logarithmic function is related to the exponential function. For example, let's consider the 2 to the power x function. I'm looking at the next page, 587. All right, and let's look at this thing for a minute here. We have first, the exponential function looks like that, okay? We have seen it in the previous section or two. So that's that. Logarithmic function is related to it in the sense that, well, you just basically reverse rows. See, for example, when for exponential function, when you plot 2 to the power x, when x is minus 3, then f of x will be 1/8, okay? Whereas logarithmic function, when x is 1/8, then the g of x is minus 3. Why? Because 2 to the power minus 3 is 1/8, okay? It's sort of a reverse action here, is the inverse function happening. And similarly, so if you do this calculation, that is, we have to, if x is 1/4, 2 to what power equals to 1/4 is what this is calculating, okay? And 2 to negative 2, 2 to the power negative 2 is exactly 1/4. So you notice that these positions are all they are related, except that you're just flipping x and y around, and which means they're inverse functions. Inverse functions means that you're constructing the mirror image of the function across the line y equal to x. That's how you create an inverse function. And anyway, so if you do that, or just plot this thing, okay, by hand, as you can see, then very soon you come up with this thing right here, and that's the logarithmic graph. Now, in general, all logarithmic graphs look that way. That is, they go down to they start down there and then swings up. That's all it does, okay? And it always crosses 1 as 0. And the reason for that is because when x equal to 1, when x is 1, 2 to the what power equals to 1? Well, that would be 0, okay? And not just 2, anything to the power 0 gives 1. So all logarithmic functions, no matter what base, it always go through 1 if it's just x. There you're going through to, and yeah, so that's what this thing looks like. And notice that logarithmic functions is defined for as x goes to 0 for the logarithmic function. The logarithmic function will become very negative, and then as a result, the x equal to 0 line, in other words, the y-axis, is the vertical asymptote for any logarithmic function. Well, that looks like this, okay? Unless it got moved, then the asymptote moves right along with it. But generally speaking, that's the asymptote is when the thing in here is when this goes to 0. Then there will be an asymptote for the logarithmic function. That it takes a dive, okay? And then on the other hand, on this side, it is while it goes to infinity very fast here, it goes. On this side it increases and will go to infinity in a very, very slow way. Okay? Yeah, extremely slow manner. Okay, because the logarithmic function grows superbly slowly. Anyway, so let's then look at the next page. Right. So now I'm on page 588. By the way, please plot this thing yourself by hand, and that is reinvent this graph, okay? Do this graph, not so much this one, well, maybe this one too, it doesn't take long, okay? Reinvent this, plot these, come up with these points, right? And then plot this graph yourself. That will give you a very clear understanding of how the logarithmic function is related to the exponential function. So please plot that yourself as well. So next, let's look at page 588, where we have two graphs here. The first one is a logarithmic graph where b, the base, is bigger than 1. That's the most normal one. Okay, and then the one here is when b is between 0 and 1. That's rarely used, but yeah, it's there. But let's please focus on this one. This is what all logarithmic functions look like. And notice that it goes through 1, 0, because any log, regardless of base, log of x, okay, it automatically goes through 1, 0, because the base to some power, but base to the power 0 is anything to the power 0 is 1, which is why this is the case. Okay, and yeah, so because we have so if this value equal to 0, then b to the 0 will always equal to 1, and that's why this works out. Let's see, maybe I should write it differently. Yeah, so I think this might be better. Okay, so if you say if x is 1, that means b to what power equals to 1? It has to be 0. Why? Because b to the power 0, okay, b to the power 0, doesn't matter what b is as long as it's positive. B to the power 0 is always 1. So see, b to the power 0 is 1 is what this means. And that's why logarithmic functions always go through the point 1, 0, regardless, that is regardless of the base, and if we are talking about log x. Anyway, so generally speaking, logarithmic functions look like that, and let's see. Okay, so let's look at the next graph. Okay, and we have the 3 different graphs. There is log 2, base 2. There's the natural log. The natural log is the log base that unusual number e. Okay, remember the natural log is the same as log base e, where e equals to 2.718, etc. E is similar to pi in the sense that it represents a fixed number. So then, and that's called the natural log. And then we have the last one is log base 10. And that's called the common log. And in practice nowadays, I have not seen the log base 10 used like anywhere. Okay, the only log we ever use in anywhere really, in math, science, anything, statistics, it's always the natural log. So log base 10 is not as common as it used to be, but it used to be very common. We used a lot, and I'll show you in the next chapter. I mean, in the next section, why that is the case, okay? But nowadays, we don't use it much, but it's left over from the past, so we still teach it, the log base 10. Although in reality, focus on the natural log, because that's basically all we ever talk about, even though the base is somewhat odd, is the 2.7 whatever that we have mentioned before, where the number come from. But but you don't anyway, so that is what you should bear in mind for now. Right now we're doing all of them, okay? Log base 2, base 10, base e, whatever, some other base. Okay, now let's look at the next page. Example 3. What are we doing here? Graph the function f of x equal to log base 5 of x. Okay, so let's graph it. So we're supposed to graph y equal to log base 5 of x. Now, to do that, we first we know that log of when x equal to 1, log is always 0. Okay, that is because so first we know that it goes through the point when x is 1, y equal to 0. And because all log functions of this that looks like this, it looks something like that, which means our graph is going to be like that. Okay, it goes here and then dives. This point here is called 1, 0. And that's about where the graph is. This is it. However, we'll plot one more point. All right, and the next thing we should say that log of being that the base is 5, okay, we know that log 5 has to be 5 to what power equals to 5? Well, 5 to the 1 power equal to 5, right? So log 5 equals to 1. In general, if the base and this number are the same, then the answer will be 1. So because the definition of log says if it equals to y, then x equal to the base to the y power. That is, this value here, the 1 is equal to, that is 5 raised to this power has to be equal to that. Well, which it does. So when x is 5, okay, x is 5, y will be 1. So at 5 and 1, this point is x equal to 5, okay, then y equal to 1. So this point is 5 comma 1 is the other point on the logarithmic graph. And my graph isn't very proportional because this much is 5 and that's only equal to 1, but you get the idea. Logarithmic graphs, log x anyway, always look this, something like this. Sometimes it might be lower, sometimes it might be slightly higher, but something like that. I should mention that log base 5 you cannot do log base 5 on a calculator. Okay, let me show you my calculator again. As you notice, it has the log, that's the base 10 one, okay, the common log, and then the ln with the base e thing. Okay, e is the number on the board, and that's it. The calculator has two of them, and even the graphics calculators online, like Decibels, you cannot do log base 5. You cannot plot it. Okay, why? Because nobody does log base 5. I mean, who in the world is going to do that? I don't see why anybody would use log base 5. Besides, everybody use the natural log. At the most, they know they'll do this, base 10, that's it. So that's why the calculator does not have log base 5. So you cannot plot this thing on the calculator and have to do it by hand. However, but being that we don't ever need it, it doesn't matter. This is just for practice. There is a way to plot log base 5 or any other base on the graphics calculator, a very easy way to do that, which we'll mention in the next section, but we'll never do that anyway, so I'm not sure why we're not going to do that very much. Okay, any other base is not sure what for. I guess sometimes it might be useful in solving exponential functions, I guess. Not really. I think we just use natural log no matter what. So anyway, so that is, but that's how you plot log base 5, even without the calculator. So next, let's look at the next page. I'm now on page 590. So let's look at page 590 where we're talking about shifting graphs. Now shifting graphs, as you might remember, if you have x plus c, then the graph will shift to the left. That's true for logarithms and any other graph you can possibly think of. Okay, it's always the case. When you do x plus c, then you'll shift from the original function, log x, okay, here's x plus c, you just move it to the left c units. And similarly, if you have x minus c, then you take the original function and shift to the right c units. Then everything shifts right along with it. See, the asymptote originally was along the y-axis. Now, in this case, it got shifted over here, c units to the left. Okay, so now it's at x minus equal to negative c. Over here, if you shifted x minus c, then the whole graph got shifted to the right. You just pick it up and move it without changing any of it. Just, carefully move it, that c units to the right. And then the asymptote, it moves right along with it. So x equal to positive c, okay, is now the new asymptote. It used to be x equal to 0. But now, because you moved it, then everything has to move right along. And that is true not just for logarithm, but for any old graph you can think of, okay? They all work this way. As we have, we already gone through the shifting of graphs in the previous section, but we're just reviewing that concept specifically for logarithmic functions. But nothing's different, okay? You apply the same principle to the logarithmic function, and as we mentioned a section earlier in the exponential function, when you shift graphs, regardless of what it is, the x plus c shifts to the left, x minus c shifts to the right. Or in these days, you just type it into the decimal calculator and it'll show you. You don't have to really think that hard and try to remember left, right. Anyway, so let's look at example 4. Example 4 says that we have a log base 3 and x minus 2 All right, so please do this example yourself, okay? We have the original function, which is right here, all right? And then that's the log base 3x, and we shift it, how do we want to shift it? -2, so we shift it 2 units to the right? -2 means shift to the right, so you do that, and there you are. And the asymptote shifts right along with it, and the new domain is now limited from 2 to infinity. The old domain used to be 0 to infinity, and because x has to be bigger than, the domain of logarithm is bigger than 0. So the new domain, being your graph shifted, now it goes from, is that a 2? No, 3? Why is it 3? Didn't it say 2? Well, whatever. The point is you shifted 2 units. Yeah, it's 2. Right, it says right there, domain is 2 to infinity. And yeah, and the range is for logarithm is -infinity to infinity, because the graph takes a deep dive down, and then it rises very slowly on the other end, very, very slowly, okay? Anyway, but it does rise. It rises slowly, but it does eventually go to infinity. It doesn't stop at some asymptote. Okay, logarithm does increase. It just does it slow, very, very slow. Let's see. So next, let's look at page 592. The same thing as we have learned before. That is, when you add a number to the whole graph, then you shift it up, right? When you subtract, you shift it down. And that's true for logarithm as well, with no difference. There's no conditions or nothing. So here's the original graph of logarithm. It goes to 1, 0. If you added this certain distance, say by d or something, then the whole thing yanked up by d. But the asymptote doesn't change, okay? Because you're moving it vertically. So the asymptote is the same one. And similarly, if you subtract it, you push the whole graph down, but the asymptote stays the same. And then the range and the domain stays the same too. And because you're moving the graph up and down, you notice it it doesn't change the domain or range. Anyway, so that's that. And let's look at the next thing. Okay, example 5. We log 3 minus 2. Yeah, this is on page 593. And so you plot the graph. Did we plot log 3? No, we plotted log 5. Log 3 looks almost identical. You just change the number 5 into 3 and you're good. But now we got to do, what was it? Minus something? I can't see where was the problem. -2. Okay, you should push the whole thing down 2 units. Okay, so what used to be at 0, now it's going to be at -2, that sort of thing. Yeah, see, it has 1, -2. It used to be 1, 0, right? And then now it got pushed down to 1, -2. Everything else is the same. Push everything evenly down 2 units, then you're done. So please do that yourself. That's example 5. Stretching. All right. Well, stretching is works similarly. Okay, the vertical stretch, like if you have here's a function, you're stretching it by a number that's bigger than 1, so your increase factor, when you multiply by a number that's bigger than 1, your number gets bigger. If you multiply by a number that's less than 1, then your number gets smaller, okay? And when you multiply a number by just 1, your number stays the same. So let's say we multiply by something bigger than 1, then your graph just stretches higher, okay, like this shows. And if you multiply by a number that is less than 1, right, what does it say? Oh yeah, it says 1 over a. That means 1 over a is less than 1. A is still bigger than 1, but 1 over a then is less than 1. And so if you do that, then the whole thing got squashed. See, the blue line is the original log, and the what is that, red line or orange or something, then it either stretched or in this case got pressed down. And the pressing happens in both directions. Okay, so as you can see, this part, when it's stretched out, this part looked like that, and then it's stretched down, this part is, the orange line got bent. See, it's more bent here, and it got poked up. But anyway, the same, the graph, other than that, the graph still looks the same. You just do this, okay? And the asymptote stays the same. The y-axis is still the asymptote, and the domain and the range doesn't change either. Okay, so that's that. Next, let's look at example 6, where it says, now example 6, we have the function log base 4 of x. That looks just like this, except that you will change the number 5 to 4. Otherwise, it looks about the same. They all look about the same. And then, but what are we doing here? We are multiplying it by 2. Okay, so then 2 is bigger than 1, so the whole thing got stretched up a bit. See, so you can see that 2 log base 4x is is twice as high, okay, as the original base 4x. And that's all there is to say about that. Okay, the asymptote stays the same, the domain and range stays the same. Right, and then so please do that yourself. Shouldn't take you long. It just stays the same. And example 7, where we do both. We have a stretch and a shift. So we will, let's turn to the next page. I'm on page 96, 596. So, on page 596, this is example, well, whatever. The point is, we have the original function. First, we have to shift it, I think, 2 units to the left or something. Left, right, something. Yeah, to the left. Because here's, the blue line is the original function. As you can see, the original functions has... y equal log x, the orange or something. Anyway, so that's the original function. First, we're trying to make it x plus 2, so shift left 2 units, okay? And then we need to stretch it by 5 units, so that's about that. So when you shift left, then the asymptote has to shift right along with it. And then the domain then now got shifted from -2 to infinity. But the range doesn't change, okay? The range still goes, the y value can go from -infinity to infinity. And then, and the new asymptote is at -2. And that's about all there is to say to that. And then reflections. Now let's look at page 597. Now, when we have reflections, means that when we had negative power. Whenever you have a graph and you slap a negative sign in front of it, the graph is reflected around the x-axis. That is, the x-axis is now the mirror, okay? And you just reflect the whole thing. Imagine the mirror image of this thing. So the blue line is the original function. And the orange thing is when you slap a negative sign in front of it. And this is true for all functions, not just logarithm. And we have mentioned this before also in the previous lesson. As in another way, if x itself is stick a negative sign right next to x, instead of the whole function, then the reflection happens around the y-axis. That is, now the y-axis is your mirror, and here's the original function, and here is the reflected thing. Okay, because whatever it used to be, it used to go through 1, 0. But now -1 is the new 1, basically. So then, in this case, in the reflection, the domain stays the same, and the range is the same, the asymptote is the same. In this case, however, the domain got flipped on this side, okay? So the domain goes from 0 to -infinity. Whereas the range is still from infinity to infinity, from -infinity to infinity. The asymptote is the same, but your graph is on the other side, okay? So because it got reflected. And that is, again, true for all functions, not just logarithm. But we emphasize that a little bit here, just to get you more familiar with how the logarithm works. So let's look at the next page, and we do example 8, where we're sketching the graph of log x. Okay, you can graph this thing in the Desmos calculator. I will show you. Well, you just to do that, you just type in log and then parentheses x, and the Desmos calculator will plot this thing right out for you. Okay, and then see, here is you plot this, and then being that the negative sign is right next to x itself, you're reflecting along with y-axis as the mirror. So you imagine the mirror image of that thing is that. Okay, everything is because -1 is the new 1, basically, because there's a negative sign. And yeah, anyways, so please do that yourself, and let's look at the next page. Example 9. Okay, now example 9 asks you to solve a logarithmic function by graph, which is, we're going to do that, learn how to do that later, like how to solve logarithmic functions, and not just by graph, okay, to actually know how to solve it. But for now, we will do this thing graphically, just to give you a chance of plotting this thing. So please plot both of these equations. This one on the first in the Desmos calculator. This one wants you to use this is talking about the graphics calculator, and which I dislike greatly, okay? We're talking about this thing here. It's horrible. I always hated it, but it is extremely painful to use. Is why I hated it. And but now they will have Desmos calculator, so please type that in. It will take you a few seconds, just as long as you can type these letters in. You type it exactly as it says, and that is, you type in 4, L, N, parentheses, X, etc. Okay, and then this thing will plot it out very nicely. Typing it into the TI-81 or 84 or whatever is much more painful, and yeah, if you have to do that, I wish you luck. So then please follow the book's instructions to do it on the TI-84 or 81, but hopefully you don't have to do that. And so let me show you what I did in the Desmos calculator. Now, as you can see, so here's what I typed in the Desmos calculator. As you can see, the red line represents 4 natural log x plus 1. Okay, you type in all these things like it says. You type in 4 L N X plus 1, and the Desmos calc will automatically know what you mean, and will automatically graph this thing right here. Okay, and you do this the same way: negative sign, a minus sign, or whatever, and 2, etc. You type that in, and that's the blue line. And then the book says we need to approximate. We don't have to approximate anything. After you do this, then Desmos will automatically show you a gray dot at the intersection. Let me make it bigger so you can see it better. Okay, now, okay, I made it bigger. See the gray dot here? After you type it in, the Desmos will automatically show a gray dot right here and here. We don't care about this one. That's just in case you care. Now, then there will be a gray dot here. Now, if you click the gray dot with your mouse, the gray dot will turn into a black dot, and it will automatically show these numbers here, like I show you. Okay, and so so that is the intersection of this thing. Now, if you don't see a gray dot, then you just click one of these equations. Just click right here, or something like that. Then the gray dot will show up. Okay, and then okay, and that should be it. So please do that yourself. So next, let's go to page 600 and look at the next example, example 10. It says, what's the vertical asymptote of some log function? Now, the vertical asymptote is always when the x value, the value in here equals to 0. In this case, or in here, okay, whatever you're taking the log of, so setting this thing equal to 0 will be the asymptote, because the logarithm cannot do 0, okay? And it's as a result, just set this thing to 0, and that's about done. In this case, what's in here is called x plus 4, and therefore x plus 4 is the asymptote, period. Okay, then we're done. So next, let's look at example 11 on the same page, page 600. We have some graph, okay, and you're supposed to figure out what is the equation of this graph, assuming it is the common logarithmic function, that is, assuming that it is base 10, okay? So then we have, first, by looking at the graph, we'll assume that the asymptote is at -2, okay? Because, it looks like it's going crazy over there. So we'll just say it is. And that is, it's going to an asymptote right there situation. So that at -2, in other words, x plus 2 is the asymptote. So we'll slap the log in front of it, okay? And then there's the stretch factor and the plus factor. We don't know what they are. and we'll figure out by substituting various numbers in there that we think is right. And first, when so let's write this thing down. Now, let me repeat that. Say that being the asymptote is at x equal to -2 or x plus 2 equal to 0, okay, that would be what's in here to achieve that asymptote. So this part, we got this part. Now we just need to figure out what a and k is. And you might think, why is there a negative sign there? No reason. We'll just, the book likes to slap a negative sign there, so we'll just do that. And it's partly because the graph looks flipped upside down. Well, whatever. It doesn't really matter. And let's find something. Where's my, okay, here's my marker. First, let's look at the point, okay? The graph appears to go through the origin. So when x is 0, f of x is 0, okay? And we'll use that to help us solve this thing. So when x is 0, so it equals to, well, first we'll do -1. It appears to pass through -1. Let me see. Well, I should follow what the book wants. Why does it? Let me think. Which one I should follow? Now let's pick the number -1, x equal to -1. The reason is -1 plus 2 equals to 1, and log of 1 is 0. Okay, log of 1 is always 0. So let's figure out, now on the graph, when x is -1, y appears to be 1. So we'll plug this point in here, -1 and 1. And when we plug it in here, okay, this becomes log -1. And that would be, the whole thing is 0. So when f is 1, that is y by f of x is 1, then this value, you plug, this whole thing becomes 0, and we become k. So just that one step, then we figure out what k is. So next we need to figure out what a is, and to calculate a is not as neat. Okay, we'll just pick 2 minus 1, which appears to be another point on here. Okay, and look at the graph. It goes from 2, x equal to 2, y equal to -1. So 2 and 1 is another point we'll choose. Well, that's what the book chose, so we'll choose it too. And that is, that's not near as exciting. We just have to, so f of x equal to, what? -1, sorry. Yeah, I knew that looked weird. Okay, so f of x now equal to, or y, okay, remember y is f of x. So -1 equal to minus a log of 4, because x is 2, 2 plus 2 is 4, plus we figured out that k equals to 1 here. So we have an equation on this. Log of 4 is a fixed number that you can calculate on the calculator. So we need to, well, do something with this, okay, and solve this equation, which means I'm out of space. Okay, so I'm going to write it out over here. All right, and here's the equation here. So then we have, I'll move the, this is the variable we're solving. So let's move the +1 on this side, which becomes -1. We have then minus a log 4 equal to -2, right? Yeah, I moved this thing over here, so it becomes -2. That should be right. Now, and then, so then, remember, we're going for a, while knowing that log 4 is just a number. We don't know what it is right now until we punch it into the calculator, but it's just a number, okay, like 5. So imagine it as 5. So if there's a 5 here, we're going to push that down across the equal sign to below the division line. So then a equal to -2 divided by negative log 4. I push the negative sign down too, okay? I mean, after all, there's both negative signs on both sides, so we can cancel them out like this. So 2 over log 4 should be the value of a. And is that? Yeah, that's all we need. We don't even need to calculate, to, you know, punch out what it is on the calculator, because the book doesn't seem to care. And if they don't care, neither do we, okay? That's good enough, okay? So the function f of x, as it written out, if you substitute that's A, the negative, don't forget the negative sign there, because originally we set up the equation with a negative sign. So negative A, which is 2 over log 4, okay? And then log of x plus 2 plus k, and k is 1. So that is the equation we're looking for. And, right. And that marks the end of this section. So please repeat all these, what was that, example 11? Yeah, so please do all these examples, okay? And that will be plus the on page 587, and that example there that doesn't have a number to it. Please plot that as well, and do all the examples, and that will be good enough for this section. There will be no homework because I don't know, it's logarithm, you know, it goes like that. Well, I'm not sure why we're even talking so much about it. So that should be good enough. So please just do that, and then we're done with this section.